Hello everybody, welcome back to another lecture for second year physical chemistry, and today we are going to discuss the Gibbs free energy and the chemical potential. What will be covered and why? We're going to cover the Gibbs free energy and the second law requirement. And we're going to do that so that we can understand what the Gibbs free energy is, and so we know how to interpret it. And furthermore, naturally, the Gibbs free energy should adhere to all the laws of thermodynamics in order to qualify as a thermodynamic equation. What do you need? The previous lectures as background. So maths, well, you'll need calculus, and within calculus we need the product rule. And from Atkins's physical chemistry, the two big sections are the second and third laws and simple mixtures. And within the second and third law section, look at combining the first and second laws and concentrating on the system. For simple mixtures, look at the thermodynamic description of mixtures. Alright, the Gibbs free energy. Let's remind ourselves of the definition of the Gibbs energy. There it is. The Gibbs energy, G, is equal to the internal energy, U, plus PV minus TS. And if you recall from our previous lectures, there you can integrate the fundamental thermodynamic identity, the equation that describes changes in the internal energy using Euler's law of homogeneous functions, and you can get a result that shows you that the internal energy equals minus PV plus TS plus the sum of all chemical potentials times the molar quantities. There it is. And what we're going to do is we're just going to do a simple substitution. We're going to substitute U into the equation for G. There it is. G is the same as it is, but we've just put in U with the definition of U. And once you've done that, by very simple cancellation of the PV and TS terms, what we are left with is that the Gibbs free energy is equal to the summation of the chemical potential times the molar quantities. Very simple derivation. So let's take a step back. So at the moment, we know the equation captures all substances in our system. And our system can be, for example, a beaker. There we are. It's a summation. But let's make this very simple on ourselves. What if we only had one substance, like a glass or pure water? What then? Well, since there's only one substance, the Gibbs free energy is just equal to the product of the chemical potential times the number of moles. And hence, the chemical potential is equal to the Gibbs free energy divided by the number of moles. I want you now to soak this in. The chemical potential is the molar Gibbs free energy of a substance. So, molar Gibbs free energy of a substance is the chemical potential. If we have more than one substance, then the total Gibbs free energy is the sum of molar Gibbs free energies and the number of moles of material. The Gibbs free energy tells us about chemical energy. That's what it is. So I can't stress this enough, that when you see the word Gibbs free energy, you should have in your mind immediately chemical potential or chemical energy. All right. Now what happens if you have more than one substance? Well, we now know for one substance this is true. Chemical potential is the Gibbs free energy divided by the number of moles. For more than one chemical species, we can say, well, let's just remind ourselves that G is the sum of all the chemical potentials times their molar quantities. And now we can just do a substitution. But we just recognize that in general, the chemical potential of any species, I, is equal to its Gibbs free energy, I, divided by the number of moles of I. All we're going to do is substitute it in, and what you get is that the Gibbs free energy is just the sum of all the Gibbs free energy, individual Gibbs free energies of the substances in your system. So let's just think back. If you just had a glass of water, its Gibbs free energy would be just equal to chemical potential times the number of moles in your glass of water. But if you had, say, vodka, which would be a mixture of ethanol and water, the Gibbs free energy of that glass of vodka would be the sum of the Gibbs free energy of the water plus the Gibbs free energy of the ethanol, which both of them in turn would be their chemical potentials times the molar quantities. So we refer to this value Gi as the partial Gibbs energy. That makes sense. It contributes partially to the total Gibbs energy of your system. As a consequence, we talk about mu I as the partial molar Gibbs energy. All right, we now have a handle on the Gibbs free energy. The Gibbs free energy is the chemical potential times the number of moles. It's the chemical energy of the system. Let's see what happens when we try and derive and see how it works when the second law of thermodynamics is applied. There's the Gibbs free equation, Gibbs energy equation, and we're going to differentiate it. dg is equal to du, that all makes sense, but pv is two functions multiplied together. So we have to apply the product rule. So we get plus pdv plus vdp. Naturally, we'll have to apply the product rule again to the TS component. We've seen this before, and there we have it. What we're now going to do is we're going to assume real systems, what is also known as non-reversible conditions. So we spoke a bit about that last week, and essentially we are going to have to put in the original definition, the one that's always true for the internal energy, which is that the internal energy is the sum of all work plus the thermal energy. And we're going to add all the string of other components that we've just derived. All right, you'll see where this is going in a moment. So we just rewrite out all the components of work. And with work, we mean mechanical work, which is minus PdV, and chemical work, which is the summation that you are hopefully starting to learn to love. We have not yet touched the thermal energy, and you'll see why. At the moment, we have assumed that this thermal energy is imparted to our system irreversibly. So we are getting a process from which we cannot go back to original conditions. So there's a real big change in the overall entropy of the universe. So that's at the moment what we're looking at. All right, we're looking at this, and we are going to do a lot of cancelling, and we are going to be at constant pressure, temperature, and number of particles. So we're looking at something very simple. So let's do that. The mechanical energies cancel out. Beautiful. Well, since we are at constant pressure, the VDP term disappears. At constant temperature, our SDT term disappears. And since we have said, well, no, there's going to be no matter added to our system or taken out, the summation disappears. And we're just left with this very interesting result. That is dg is equal to dq minus tds. All right. So what's going on? What's our big conclusion? Well, the change in the Gibbs free energy at constant pressure and temperature is equal to the thermal energy minus the temperature times the change in the entropy of the system. Now, if you remember back to the very first lecture, there's the Clausius relation for the entropy, which is equal to this. Remember that inequality. If it's greater than, if the change in the entropy is greater than dq on T, you have an irreversible process. If it's equal, then you have a reversible process. So we do a substitution, or we recognize actually that the change in the Gibbs free energy has to be equal to or less than 0. And this is one of the big conclusions I hope you would burn into your memories, is when it comes to the Gibbs free energy, if you want to know whether something is going to happen to your chemical system, all you have to ask is does it minimize the free energy? Why is it minimized? Notice this change, this dg function, has to either equal 0. If it's 0, nothing is changing. If it's less than 0, that means your dg is a negative number or a negative value. Then clearly your Gibbs values must be decreasing over time. So that means you are minimizing or decreasing your energy till you reach no change. That's a minimization behavior. So hopefully also you get to see the difference between what is a reversible process and an irreversible process. A reversible process is when that dq equals TdS, and so your change in the Gibbs free energy is 0. In essence, a irreversible process means you doing things to a system such that the Gibbs free energy the change in the Gibbs free energy stays 0. All right, big key concepts to take away. 1, the Gibbs free energy tells us about the chemical energy of our system. The change in the Gibbs free energy dg is equal to the sum of mu I times dn. Once we account for integration, we find out that g is just equal to the sum of mu I and I. And from it we learn that the chemical potential is just the Gibbs free energy divided by the number of moles, and hence it should be thought of as the partial molar Gibbs free energy. Furthermore, all chemical systems will try and minimize the Gibbs free energy. And this is imparted by the equation here, which states dg at constant pressure and temperature is equal to dq minus tds, which is either equal or less than 0. All right, this brings us to the quiz question. Question number 1. The Gibbs free energy of formation for diamond and graphite are 2.9 kilojoules per mole and 0 respectively. Which do you expect to exist at ambient conditions thermodynamically? A, graphite, B, diamond, C, both. And question number 2, the chemical potential of water is minus 237.14 kilojoules per mole at ambient conditions. Determine the Gibbs free energy at ambient conditions for 100 milliliters of water. Give the answer in kilojoules.